Hey guys, my name is Garrett and I'm a tutor for AP Calculus AB, BC, Physics B, C, Macroeconomics, and Psychology. So a little bit about me. I've been tutoring for the Engineering Peer Tutoring Service at McGill for over 2 years now. I specialize in Calculus 1 and 2, as well as linear algebra. Many of the courses that I tutor, I've had a lot of experience with. For example, Calculus 1 and 2. I took those in high school and I've just completed Calculus 4. And many of the concepts that you learn in these courses are the fundamentals for these more advanced courses. So I've had a lot of experience with them since taking them, and we'll have a great time tutoring them.
Hey guys, so I found this problem online, and it's actually quite similar to what you can expect on the AP exam. So let's get started. A 20 kilogram box on a horizontal frictionless surface is moving to the right at a speed of 4 meters per second. The box hits and remains attached to one end of a spring of negligible mass, which other end is attached to a wall. As a result, the spring compresses, maximum distance of 0.5 meters, and the box then oscillates back and forth. Okay, so it looks pretty straightforward. But let's draw a picture to start. Okay, so we have our box moving to the right at 4 meters per second. And here is our spring, right? So let's split this up. Okay, so initially, are there any forces acting on the box? So it's moving to the right, 4 meters per second, and it has not collided with the spring yet. So actually the answer is no. There are no forces acting on it. As we know, it's a frictionless surface, right? And it's also moving at a constant velocity. So therefore we know there are no forces acting on it. The second part is when it collides with the spring. Okay, so here is our box. And this is the moment of impact, all right? So as you know from previously, there's going to be a force from the spring that's proportional to the distance of compression as well as the spring constant. Okay, so let's take a look at part A. The spring does work on the box from the moment the box first hits the spring to the moment the spring first reaches its maximum compression. Indicate whether the work done by the spring is positive, negative, or zero. All right, so the way that I think about work is in terms of direction of objects, right? So if the force acts in the same direction that an object is traveling in, then that does positive work. You know, it adds to its energy, it adds to its velocity, right? If it's in the opposite direction, then it will be negative. Okay. Well, in this case, you know, our box moves to the right, and it compresses the spring, right? So, object was moving to the right, and the spring will push back the force in that direction. Remember, as we said with kx. Okay, so this shows us that it is actually negative, doing negative work, right? From the moment that it hits the spring, it will decrease the velocity and decrease the kinetic energy of the system. Okay, let's take a look at part 2. Calculate the magnitude of the work described in part 1. Okay, so work, we can kind of think of it as energy, right? So the change, if it does work on the system, it will either add energy to it or take away. Because the object is moving, we can think of it as the change in kinetic energy, right? So the initial kinetic energy of the box is 1/2 mv1 squared, and then minus the resulting velocity, right? Start kinetic energy. We know these values. It's 1/2, 20 kilograms, and it's moving at a rate of 4 meters per second squared. 1/2, and then 20. Okay, now here's the tricky part, the second velocity, right? We know that there will be 2 stages for this box. So let's draw another picture. So there would be this part where the box first makes contact but doesn't compress, and then when it compresses all the way, the 0.5 meters, so we can kind of draw that, 0.5. So here it's moving to the right, and here this is the point where it stops moving, right? It stops moving because the spring pushes back and it's going to move in this direction, right? But it's not yet moving, okay? So then at this point, the kinetic energy is zero. Sorry, the velocity is zero, which leads to zero kinetic energy, right? And we can calculate this. It's just a simple calculation, 160 joules. By the way, don't forget your units because they'll take points off for that. Okay, so part B, calculate the spring constant of the spring. Okay, so an easy way to do this is because we've already used energy in this part up here. So we should continue to use energy in this next part, right? So we know that the potential energy of this system, so it's U is typical notation, will be equal to 1/2 k x squared. This is the potential energy of a spring, right? And we know from our laws that the energy of a system does not change. It stays constant unless an external force is applied to it. So this will still equal 160, equal to 1/2 k x squared. Okay, but the assumption that we're making in this case, right, is that all of it is in potential energy. So that means that when, this is when the spring is fully compressed, right? When it stops moving, it has no more kinetic energy, right? So this will be at maximum compression. So this will be 160 equals 1/2 k and 0.5 squared. Okay, solving for k, we get, let's see, 1,280 joules. Sorry. This is spring constant, so this is newtons per meter. Okay, cool. Next part. Calculate the magnitude of the maximum acceleration of the box. Okay, so we know from before that the force is equal to kx. So why do we want to calculate force? Well, because we know from Newton's first law that the force is proportionate to the mass times the acceleration. Okay? So we know the spring constant, we know the maximum, and we know the compression, right? An important thing to note from part C is that where the maximum acceleration occurs, right? So we can go up to our diagrams up here. Okay, I'm gonna change my color. Here, there is no, in the first picture, there's no acceleration, right? It just comes in contact with the spring, right? And then in part 2, it compresses, and then it reaches its maximum compression, and then it pushes back in that other direction, right? So this is the point of maximum acceleration, right? Because the force is the greatest, and because the spring is compressed the most. So we can now plug these values in. So F is equal to kx, so we know that k is equal to 1,280 newtons per meter, and the distance is 0.5 meters, so then we get 640, okay? And then, sorry, kind of running out of room here. Force is equal to mass times acceleration. We know that to be, we'll reorganize this. So then the acceleration will be the force over the mass. And we know both these values, so it will be 640 divided by our mass of 20, which gives us a value of 32. Okay, our acceleration is 32 meters per second squared. Okay, cool. So part D, calculate the frequency of the oscillation of the box. Okay, so they always like to throw these questions in. Typically, you would just memorize the equation. You'll see later, but we can actually derive this. But the equation will be the frequency, it's 1 over 2 pi k over m. Okay? So something to know is proportional to the spring constant, and it's inversely proportional to the mass. Okay? So don't worry about this equation. We'll discuss this later and explain why this is. Okay, so 1 over 2 pi is k We know these values, 1280, and our mass is 20. Okay, and we calculate these values, so that will be 1.27 hertz. So that one is basically just a plug and chug. Don't worry about the equation, we can discuss that later. All right, so I hope you guys enjoyed and learned something new. That's about it for this.